Okay, this video is about Hess's law and Hess's cycles. Okay, so Hess's law. What is Hess's law? If a reaction can take place by more than one route and the initial and final conditions are the same, the total enthalpy change is the same for each route. So what does that mean then? So we always start at reactants and we end at products. So if for some reason going directly from these reactants to these products, that reaction for a variety of reasons can't be measured, if we know what if we can instead go from the reactants to an intermediate, and then from the intermediate to the products, that will be the same energy change going from here to here to here as it is going directly from here to here. As long as we start and end with the same things in the same states, then the total energy change will be the same. Okay, you don't have to do the direct reaction. You can do an indirect reaction, and then you can do a combination of many reactions if you wanted to, several reactions. But as long as you start and end in the same place, the total energy change or total enthalpy change will be the same. So in this case, this reaction here is called A, and this one from here to here B, and this one C. A is the same as doing B plus C. Okay, the total energy change will be the same. Because in both cases, going from here to here, we start off with reactants and in products, and from here to here to here, we start off with reactants, and we eventually end up with products. We just take an extra step, but the total enthalpy change will be the same. Okay, so first of all, we're going to look at a Hess cycle using enthalpy of combustion values. Right, so here's a table. They've given us some different substances here, and this is the enthalpy of combustion for each of those substances. So when you look at this, you've got to think carefully about what that means, the enthalpy of combustion. Remember, the enthalpy of combustion is the enthalpy change when you burn 1 mole of a compound completely in oxygen. So carbon plus oxygen would make CO2 in case of the first line. So that's the reaction that's occurring, and when it does, it releases that amount of energy. Okay, so it's also an exothermic reaction. 1 mole of carbon, reactive oxygen to make CO2. The CO2, what we're going to look at in a second, is we're going to use this table on this equation here. And this equation is not a combustion reaction, but we're going to use combustion values to work out the enthalpy change for it. Okay, this reaction is very hard to do in a lab and measure the enthalpy change, because you've got to get carbon, hydrogen and oxygen to react and only make, in this case, ethanol. Well, there's a whole variety of things they could make. So to get them to react in those ratios to just make ethanol is virtually impossible. So it's a theoretical reaction, but we're going to work out its value by using these combustion values, because these reactions, combusting these three things, is very measurable and very doable in a lab. Right, so we've got carbon, hydrogen and oxygen reacting to make ethanol. Nowhere in that reaction is any carbon dioxide. Okay, let's think about what this one would be. Hydrogen, enthalpy of combustion, that would be H2 plus half O2 making water. Okay, nowhere in here is really water. Okay, if you burn ethanol, you make carbon dioxide and water. So again, no carbon dioxide, water in here. So the carbon dioxide and water must be part of the intermediate. Okay, this part here down the bottom part of the Hess cycle. So whenever you get combustion values like this, okay, it's the combustion products which go down here at the bottom. The reaction you want to find out about, the enthalpy change you want to find out about, just goes along the top here. But in this case, with combustion values, this isn't combustion, it's irrelevant what this is here, but what's up here, the combustion values, the combustion products would go down here. So when I combust carbon, I make carbon dioxide. When I combust hydrogen, I make water. If you notice, there's no value for oxygen here, and that's because you can't get an energy change for oxygen reacting with oxygen. It's not a reaction that occurs, so we can just leave that out, that's fine. And then here we've got ethanol, it combusts, it makes carbon dioxide and water. So these arrows here, this one and this one, are pointing down, because the reactions that we've got here are producing the things in the middle here. Okay? So we can't work out this directly, but we can go indirectly. So this arrow is showing that we go from here, around and up. So we can work out what this enthalpy change is of these being combusted to make this. So we do 2 lots for the carbon that I'm getting from here, 3 lots for hydrogen from up here. Like I said, the oxygen, you can't combust oxygen in oxygen, so we can just leave that out. And then that gives us that value there. Okay, this one, there's only one of them being combusted, so it's taken directly from here and that's put in there. Okay, so the entropy of formation then is we take this value, because we're going in the same direction as this arrow. Okay, combustion arrows point downwards towards combustion products. We're in the same direction as that one, but then we're going in the opposite direction of this one. So we put a minus in front of it there, so it's minus minus. Okay, because that's already a minus number there. Because we're doing this reaction in reverse. Okay, the opposite of combustion of ethanol. Do that sum, and then we get that value there. Okay, now sometimes rather than giving you combustion values, they give you formation values. So if we just skip to this one here, this is the reaction we want to find out about. 2 moles of nitrogen monoxide reacting with oxygen to make 2 moles of nitrogen dioxide. Now, this is another reaction where it's hard to measure because there's many oxides of nitrogen, and doing this reaction you can get all different products. So this is not a formation reaction, this is not actually really a combustion reaction, it's an enthalpy of reaction. Okay, so what have we got here then? We start off with 2 moles of NO. So here's NO here. Now what we've got here is enthalpy of formation values. So let's think about what that means again. The enthalpy of formation of NO. Think of the definition. It's the enthalpy change when 1 mole of a compound is made from its constituent elements in their standard states. Okay, so it's made. The NO is the product of this reaction, not the reactant like we saw with the enthalpy of combustions. Same here with NO2 would be here. So NO and NO2 are in our equation, but these elements that make them aren't. So it's the elements that go down here in the bottom part of the Hess cycle. And the arrows will point up from the elements to the things that they make. If you notice, there's no value for oxygen, because oxygen is an element, so you can't get an enthalpy change from making oxygen from oxygen. So again, we can just leave that out, that's not a problem. So we're making 2 moles of NO from its elements, so it's double that, so it would be 180. And we're making 2 moles of NO2. This is just to make 1 mole, because it's the standard enthalpy of formation, so we times that by 2, so 2 lots 33, 66. Now again, we're starting from here, and we're going round and then up, okay, like we always do. So this time, the first part we're doing in reverse. Okay, we're not going that way, we're going this way. So we're doing this reaction, but reverse, so it's just reverse the sign. So that's why I've got minus 180 here. But this one I'm doing in the same direction, so we can just use the 66. So 66 minus 180 gives you minus 114. So the important thing with both Hess cycles is to concentrate on the table and think about what does that value mean. Write out an equation of what that value means, and then write your Hess cycle.